Hi, I'm Elizabeth Blenk, a student in MAE 535, Design of Electromechanical Systems at North Carolina State University with Dr. Buckner. And this is our demonstration project analyzing magnetohydrodynamic propulsion.
The Lorentz force is the resulting force acting on moving charges in the presence of electromagnetic fields. For a straight stationary wire, the Lorentz force can be calculated by determining the cross product of the current with its associated length vector and the magnetic field, such that the Lorentz force will always be perpendicular to the magnetic field and current. Modern electric motors rely on the Lorentz force to move electrons in a solid moving rotor. However, this same principle works using ions in electrically conductive fluids known as magnetohydrodynamic drives. The flow of fluid resulting from the MHD drive is dependent on the number of ions in the solution, the strength of the magnetic field, and the strength of the electric field.
Our first experiment was a small-scale proof of concept. In this setup, 2 copper wires were held at the ends of a AA battery, and the other ends were placed in a small glass bowl filled with salt water, with a permanent magnet under the bowl. The expected field and force directions can be seen in the image on the right, where the blue arrows are the magnetic field lines, the purple arrows are the current, and the green arrow is the predicted Lorentz force. As the Lorentz force acts on the ions in the solution, fluid flow occurs. The current flow was faster than expected with the limited power supply. In this demo, bubbles being produced at the surface of the wires are caused by electricity decomposing water into oxygen and hydrogen gas.
After a successful proof of concept, we wanted to explore changing the various design parameters governing the MHD drive. The setup used 2 angled aluminum brackets placed in a plastic container with 10 cups of salt water. The aluminum brackets are connected to a variable speed model train power supply using alligator clips. Under the container was a large permanent magnet. This setup provided a simple way to vary design parameters and see how they affected the flow of the liquid.
In this experiment, we varied the space between the brackets to see how the speed of the water is affected. To calculate the speed, inches were marked on the angled aluminum, and the amount of time for the small foam pieces to travel 1 inch was calculated. 3 inches was the largest gap analyzed, and 1/2 an inch was the smallest. As the gap decreased, we saw the speed of the fluid increase. The decreased distance between the brackets caused an increase in current, which also causes the force on the ions to increase by Lorentz's force law.
In this experiment, we increased the voltage across the angled aluminum. We expected that as the voltage supplied increased, the speed of the fluid would also increase. However, the calculated time for the water to travel 1 inch is slower in the video with the higher voltage. This inconsistency could be caused by an unreliable power supply, issues with the bottom of the plastic container flexing and producing spaces for water flow to escape, and inaccurate measurement technique.
In these 2 videos, we show that as the distance from the magnet increases, the force produced decreases. We accomplished this by using different height spacers under the plastic container. The time taken for the water to travel 1 inch is significantly reduced by increasing the distance from the magnet. We did run into some issues with our floating pieces being attracted to the angled aluminum. This could be because the styrofoam held a charge and was attracted to the bracket.
In these 2 videos, we show how altering the direction of the current can change the direction of fluid flow, as the Lorentz force is determined through the cross product of the current and the magnetic field, and thus must follow the right-hand rule. The direction of the current was altered by changing the positive and negative terminals on the bracket.
Similarly, in these 2 videos, we show how altering the direction of the magnetic field can change the direction of fluid flow, as the Lorentz force is determined through the cross product of the current and the magnetic field, and thus must follow the right-hand rule. The magnetic field was changed by switching whether the north or south pole was facing the brackets.
In this demonstration, we explored the relationship seen in the Lorentz force equation. If we were designing a system using magnetohydrodynamics, we would want to produce the highest Lorentz force possible. As seen in these demonstrations, to accomplish this, we would want to maximize the voltage applied, minimize the distance between the magnetic and electric field, and minimize the space between the aluminum plates. We also showed that the Lorentz force is directional, and by switching the direction of the electric and magnetic field, the direction of fluid flow can also be switched.
Using an MHD drive is advantageous as it produces a flow of fluid without requiring any moving parts such as a pump or a motor. Therefore, it could prove to be useful in applications such as through driving boats and submarines. However, it is far from the stealthy MHD drive submarine seen in the 1990s film A Hunt for Red October due to the electrolysis and the underwhelming force produced. Ongoing research is looking into using plasma to ionize the fluid to produce more force.